不管你跑去哪里，然后你都是会去接近你自己真正喜欢的事情。好，开始直播。So we start the live stream. We start the live stream. Okay, so then I don't do a little recap. We start to mention Ampere's law last time. So this is Ampere's law. And today we are going to apply the Ampere's law to analyze complicated structures. And the Ampere's law, this is just a reminder for you. The mathematical form is kind of simple. It's saying that the magnetic field, and this is how you go with your loop integrals. So this is magnetic field, and this is the vector for the loop integral. If you take an inner product of them, and then if you just integrate them along a closed loop, and be careful, this loop should be closed. So here we have a little circle here. If you just do the integration like this, then the number right here, should be equal to a magnetic constant multiplied by the amount of current. So it's a little bit like you are creating an imaginary circle and surrounding a bunch of current. So if you do the integration like this, and it's a quick way for you to get the strength of your magnetic field. But I think you can just imagine this Ampere's law is very limited to the simple structures. And what about complex structures like these two guys? So we have solenoid. This is solenoid, and we have toroid. This is toroid. And solenoid, you can see I just especially pick a structure like this. The solenoid is this one. It's the loop of wires, and which looks like a spring. So this is solenoid. But you can see here, this is the material that you insert into the solenoid. Usually we put ferromagnetic materials inside because they have higher magnetic coefficient, and then you can create stronger magnetic field from it. So that is how we apply solenoid. And our question is, how does the magnetic field look like around a solenoid? So we're going to do the analysis later with two different approaches. And one of the approaches from the integration, the other one is from the Ampere's law. So we are going to analyze it from two different directions, but finally we get into the same answer. And for the toroid, this is like a solenoid, but you bend it over, and then you attach the head and the tail together and create another ring. And this is the structure called toroid. And again, you can put in different kind of materials into the center of your toroid, and then you can change the strength of your magnetic field. If you put in ferromagnetic materials, then the strength of your magnetic field can get increased in several orders of magnitude. 2 orders of magnitude or even 3 orders of magnitude, so you can create such a strong magnetic field by this kind of method. So let's get started. 这个 solenoid 是螺线管，然后Toroid 我发现在中文里面，上次有问过，对不对 ？Toroid， 然后就真的没有一个中文名字，不然我们有时候叫它环形螺线管，或者是你就用笔的，就是那个。对，可是这个东西 ，but this is very very common in electronic engineering. You can see it everywhere, small ones and big ones. I don't know, we just call it toroid. 我不知道我们在中文这个在做这个电子电路的人常常用到但是我们好像都直接叫它 toroid， 好像没有人讲环形螺线管，或是我们就讲什么甜甜圈，或是帮它取一些奇怪的名字。 对啊，反正就是会，我们就说那个一圈一圈的，对啊，我们就好，所以这个英文的名字叫 toroid。toroid 在数学上面是一个很专有的名词。The word toroid is a very professional, specific word in mathematics, especially in topology. 就 toroid 它其实在拓扑学里面是一个很专有的名词，就是有一种部分特别的几何形状，然后那个线这样子绕着那个形状，那种分布，那个叫 toroid。所以在数学上它其实是一个非常专门的名词。Okay, so this is the introduction for solenoid and toroid. Okay, we start from the complicated approach, but from the complicated approach you can have more information, and you don't apply too much approximation. So that's the good thing for the complicated approach. 我们先从比较复杂的取向开始。那比较复杂的取向，它的数学就是很琐碎。可是呢，因为你并没有做多余的简化，所以你可以用这样子的方式去处理很复杂的问题，并没有什么资讯会流失，然后你也没有跳进什么结论之类的，就你没有先射箭再画靶啦。但是如果说我们之后会再跟你介绍一个是用安培定律去做的，那个就有点是先射箭再画靶的味道。但无论如何呢，我们就是2个取向我都会带你去做一次。那今天复杂取向没有在课本上，所以如果你想要看完整的解说的话，你可以就是把我们课程的投影片下载，然后这边有一个网址，你就去搜寻这个网址，然后它里面有完整的说明。So today the complicated approach is not on the textbook. I copied it from an open textbook, so you can get on the internet, you can download it and you can read it. It's totally for free. And this is called physicslibertext.org. And here's the chapter number, so you can check the detailed explanations and the detailed derivations on that kind of word page. And I really recommend you to use this one as your second textbook. I think this is really good because it's like people just contribute the knowledge for free and just collect them into a textbook, so you don't need to pay anything, but you can get all the information here. That's really good. 就 LibreText 其实是它是好几本课本的集大成，然后你上去看那个课文的话，你是不需要付钱的，完全免费。然后也是大家就是直接像 Wikipedia 一样，大家就是直接贡献自己知道的东西，然后把它凑成一本 textbook， 我觉得是蛮好的。我还蛮常参考这个网站，有兴趣的同学你可以把它 bookmark 起来，就是你可以用那个浏览器书签，你可以把它存起来，这个很好用，以后你可以常常用。好 ，Then we start the derivation. This is the shape of our solenoid. So here's a wire. The wire goes this way. It spins like this and go out this way. And our current is going into the wire from here and get out of the wire from here. And you can think about the direction of the current flow on the solenoid. You can think about it in your head for a while. And here is another parameter. This is the length of our solenoid. So we have a limited length. So if you take a knife, if you cut your solenoid in half, just cut it like this. So cut it from here and cut it into 2 halves. And if you look at the cross section of your wire, you can see that in this configuration, our current is going into the wire on this side, and the current is running out of your wire on this side. 所以你如果把你的螺线管切一半，然后呢，你探那个截面，你就会看到你的右手边，你所有的电流都是流进去，就是从纸面穿进去，然后你的左手边所有的电流都是从纸面穿出来。 然后这边是有一个 so we have a special symbol here for this kind of vertical configurations. If it's going into your pages, then we mark it with the cross, and if it's going out of the pages, then we mark it with a dot. So this is a common sense and everybody uses it, so you can use it too. 这是大家约定成俗的符号。就如果说你有某一个向量是从纸面穿出来，然后我们就打一个点；如果这个向量是从纸面戳进去，然后你就打一个叉，这样我们大家就知道了。Okay, so now we have to think about it in a three-dimensional mindset. Yeah, and here's another parameter, r. The capital R is the radius of your solenoid, and here are some angles that we're going to use it later. Okay, then we start from we just derived we just made the derivation here. For a single loop of wire, we can just take the single loop here. And maybe we are standing somewhere on the axis, and we would like to know what is the strength of the magnetic field if I measure it. So we just did the derivation here. We just finished the derivation in the last lecture, so we can go back and you can check the derivations. But now we just take the result and we modify it a little bit for our solenoid. But in this case, you can see the radius of your ring is A. And I'm saying here the distance between my measuring point and the center of the ring is X. Okay, let's do the translation. And now we are in a solenoid with new symbols. So this is the original text. And now we are going to do some modification. First of all, the modification is about the current. Now we have an array of current. So we have an array of current. It's not a single loop anymore. So it's like a wall of current. Okay, so now we would like to apply the density of current, and this is how we calculate it. We have this is the number of coils here, so this is n. We have n coils here. 我们有 n 个 current loop， 我们有 n 个 current 圆环，所以这是 n and L is the length. So number divided by length, this is the number of current rings in a unit length. Okay, and we multiply it by the single current, the current on a single ring, and then we multiply it by the y. So this is a little piece of length on the axis direction. So this is how we define the current in this case. So 这边你可以看到说 dy 除以 L 就是比例，我们一个 dy 跟你整条螺线管的之间的比例，然后 I 乘上 n 就是这一排所有的电流加起来。This is another way to think about it, so don't get confused. So I multiplied by n is the number of current on the wall here. And dy divided by L is calculating the ratio between a small section for your integration and the total length. And by this, you are actually calculating the density of your current. And then we put the current, the radius, and the positions into the text here, and we change the parameters into the parameters for the solenoid. So this is the magnetic field created by a little piece of current ring. This is the current running on the ring, and R squared is because this is a and you get a squared, but now replace the diameter of your loop into this one. So we get r squared, and 2 is because the 2 pi a and 4 pi, they just cancel each other. We get 2, and y is converted from x here. So that was x in the previous calculation, but now we change it into y. It's just changing the number. And r squared is replaced for the same reason, and the others are roughly the same. Okay. It takes some time to convert this one to this one, so you can do it at home when you are in peace and when you are calm. 就要花一点时间，就是你的参数转换要花一点时间想。我那时候也花了大概20分钟，我才想通它到底在干嘛。所以你现在如果觉得有点困惑，没有关系，你回去你再慢慢想。Then, okay, here's the arrangement for the parameters. We would like to separate them into coefficients and variables. So here this is the coefficient. Here are the coefficients and constants. It's not affected by our integration. And here's the variables. So here's the variables that we're going to integrate. And mu 0 r squared, and di is replaced by this one. So that's the reason why we get n over l here, and 2. And now we are integrating on the y direction. So for the variables, we have dy, we have y squared plus r squared, and here is the power of 3 over 2. Constants and variables. Okay, so it takes a lot of work to do the arrangement for the equations. 所以我们从这一步到这一步，我们做的事情是，我们要把一团乱的东西，我们要分清楚哦。哪一个是常数，哪些是常数，然后哪一些是参数。常数你可以把它放在一边，参数你放到另外一边。参数就是我们在做积分的时候，我们要积的东西是参数，然后常数就是那些不受积分影响的。那我们把两边分开。好，所以 then if it's okay, then we go next step. Here we have to do, we have to step out a little bit, and then we have to analyze another thing. We have to analyze the geometry. So we look at the geometry of the solenoid. This is the cross-section of the solenoid. If we are measuring the magnetic field, say here. So this is y. And here are some angles which is related to the beginning and the end of the solenoid. And here this is the theta. Theta is actually equal to y divided by, y is this one, divided by this one. So this is how you convert, let's say, we are converting xyz into theta. 所以我们这里我们要做的事情是把 xyz 把长度转换成角度。好。所以我们这边是第一个转换。So this is our first conversion. So we get the sine theta. And if we do derivative on the sine theta, we have cosine theta d theta. I expect that you are very familiar with this kind of conversion, so I don't explain it why is it like that anymore. And here is the derivation on the other side. Okay? So in the process, then you can check the handbook, then you will understand why it finally gets to this way. So you can just you can do the derivative by yourself. Then finally you have this one and this one. Oh, it looks so complicated. But if you again do a little bit, if you just make the denominators just exactly the same, and then you can regulate it a little bit, and then if you combine them together, you will get this one. So you get cosine theta d theta is actually the r squared dy divided by y squared r squared and 3 over 2. 中间那个一步一步我就不带了， 这个是你可以回去看一下那个或是上网 Google 一下你的微分表跟积分表，然后你看一下你就会知道为什么。好，所以这边我不再一步一步讲。好，你回去可以自己练功一下，没有很困难啊，就是一个 u 除以一个 v 的时候，然后你做微分 u 除以 v 呢，你要怎么微是有公式可以套的，没有很困难。Okay, so r squared dy and this one, and we just go back and check our equations here. R squared is right here. Dy over this complicated guy is here. So if we just take them out and then replace it by cosine theta d theta, then it gets very simplified. 所以我们就回去这边哦，我们去看这边，你会发现这边对这一块跟 R2 这一块。我用浅蓝色标示的，其实就跟它讲的是一模一样嘛。然后我们就可以把那些蓝色的底全部换掉，我们把它换成 cosine theta d theta. So we can just analyze the equation here, and you can see the parts in the blue shades is just exactly the same as the cosine theta and d theta. So we can just replace them, and now the variable y is converted into variable theta. Okay, it makes the integration simpler and easier. And then the next step. Okay, then we do the integration. We integrate it from theta 1. So this is from the bottom side. And we integrate it to the other side. This is the top side. So, sorry. We integrate it from theta 1 to theta 2. Theta 1, theta 2. And the integration of cosine theta gives you sine theta. And this is the lower limit and upper limit. And just by applying this equation, you can calculate the magnetic field in any places, at any places and with any kind of length. 你如果用这条公式的话呢，你就可以计算，你就完全没在怕。不管你的螺线管长度是多长，不管你现在测量的点是在螺线管的哪里，你都可以用这条公式把磁场算出来。但是呢，它有一点点，它有个小限制，就是你的测量点一定要在螺线管的轴上面，你歪一边的话，这个就不行。好。But here's the limitation: you have to stand on the axis, the axis of your solenoid. If you're a little bit deviated from the axis, then it doesn't work. But anyway, you can stand just inside your solenoid, or you can stand far away. And you can calculate the solenoid in every kind of length. So this is very versatile. And the next step is, let's check if it makes sense. So if the solenoid is very long, now we're doing an approximation, an infinite approximation. So if the solenoid is very, very long, then theta 1 is equal to minus pi over 2. You can imagine in your head, if you have a very long solenoid, then your theta 1 is approaching to an angle like this, isn't it? And theta 2 is plus pi over 2. So an angle like this, if you have a solenoid with an infinite length. Then you have a 2 from the integral. This just vanished. Then we have this one. Simple. And all the magnetic field is running on the y direction. They are parallel to each other. And n over L multiplied by I. This is simply the total current. No, the current density, sorry. This is the current density on the solenoid. 所以 N 除以 L 乘上电流 I， 它是你的螺线管上面的电流密度。 等一位同学还在正笔记书。OK 了，那我们再往下。And here's another approach. Here we started from BO Savat law. 这里其实我们第一个 approach， 如果你记得我们这里在干嘛的话，我们其实是从 BO Savat 定律一路一直推导过来。好，艰苦奋斗。然后再来呢，第二个我们要用安培定律。这个安培定律就有点透视过，有一些对于理论很钉钉的人会受不了，但是这个是你在实务里面就很好用的一种想法。So this kind of if you are applying Ampere's law and actually you are making a lot of pre-requests and you are making a lot of approximation, so those are really picky with the theory and those are very picky with the process and they can take this, they just find this ridiculous. But this is very easily used when you are in a lab or when you are really working with devices and when you need a quick approximation. So this is a good method to use too. So we are sticking ourselves with the long solenoid or thin solenoid. 这里我们就维持着我们现在在处理的是一个很长的螺旋光，不是一根很细的螺旋光。那么 then how do we apply Ampere's law? So we already know, this is the prerequisite, we already know our magnetic field in the long solenoid should be like this. Should be straight, they should be approximately parallel with each other, they should be in the same strength. So this is the prerequisite. We take it as something that we already know. Then we apply Ampere's law. So the Ampere's law is saying that if we create an imaginary closed loop and we hold the current in the closed loop, then it should give you a number which is proportional to the number of the current. So the closed loop is setting up like that. This one, the pink closed loop, then it's closed. Then we can divide it into 4 sections. Section 1 going from here to here, and the inner product of your magnetic field and your path is just this one, B multiplied by the length. Here your vector B is always parallel to your vector ds. That's the reason why if you walk from here to here, if the distance is the L, then this is just BL. And then you take a right turn. This is the second section. On this section, the B and the S are perpendicular to each other. Okay. They are perpendicular to each other, so vector B dot vector ds gives you 0. Yeah, correct. And if you walk outside, and there is no magnetic field at the outer, in the exterior region of your solenoid. Just remember we have a very long solenoid, isn't it? So, 所以这边呢，大家要注意，我们现在处理的是一个长度是无限长的螺旋光，所以我们才可以说外面这边的磁场是没有的，实际上是有的哦。好，所以如果你的螺旋环的长度是有限的，其实是会有的。So, but just be very, very careful. If you have solenoid with limited length and then the passage 3, and it shouldn't give 0. It should have some other number, but not this one. So you have to be very clear about this is an approximation for a very long solenoid. So for the 4, and we get 0 for the same reason as the section number 2. And by the integration, we just get exactly the same number that we get from the integration form. And just a small reminder, so actually the magnetic field going this way is returning this way. If we have a short solenoid and it's a little butterfly, but if we have a long solenoid then it's a very big butterfly. And the strength of the magnetic field here is very, very, very weak. And we just take it as it's negligible. So that's the reason why the section 3, we can just take it as 0. 然后就是这边，这个大家可以看一下，就是它的形状其实是像这样。然后你的螺旋管的电磁场形状，它其实形状是有点像蝴蝶。那如果你的螺旋管长度是有限的，然后呢，你的磁场线这样出来之后，它很快就会转弯，然后就转一圈又回来。但是如果你的螺旋管很长的话，然后呢，你的磁场呢这样延伸出去，它要转很大一圈才会回来。然后这边的磁场很弱很弱很弱，弱到你可以几乎不要理它。所以这就是为什么我们可以这么粗暴的使用安培定律，我们就把这边3，我们把它当成是0。那是因为已经有人帮你做过这件事情了，他告诉你，这里会平行，这里会很弱，所以你可以简单粗暴的使用安培定律。好，所以这样子的说法，有很多人会觉得不舒服。不舒服的原因就是因为这边为什么是平行的，这里为什么没有？答案是因为人家已经帮你分过了。好，这也是大家在看课本的时候常常会觉得很痛苦的地方，所以我这边帮大家解释一下。So usually when people start from the textbook, and the textbook usually directly jump into a law like that, and some careful students get really confused because they would like to have a proof. Why is it parallel and why is it weak and negligible? So the answer is because someone did the calculation by the integration form before. They already know the answer, and then they simplify everything into a form that you can apply Ampere's law. So that's the reason why. And this is simple, and this is a very brutal approach, easy to use. So yeah. Okay, so for the solenoid, but let we just take a deeper look into it. So the solenoid, if you look at the structure of the magnetic field in more details, and actually we demonstrated in the video last time, isn't it? So every single loop of the wire is having a magnetic field circular like that, and it's circling around each wire. But if you look at all the wires and all the magnetic fields are circling in the same direction. So if you draw your magnetic field lines in a way like a equal potential line, so it's the equal field strength line, and you can just link all of them together if they have the same strength. And this is the reason why that when you are getting into the center of your solenoid, then you can approximately think about your magnetic field as if they are straight and as if they are evenly distributed. But actually they have complex little structures. So you can see the mindset in the Ampere's law is too simple, and this is too much violence, in my opinion. But if you have this picture in your mind, then you don't get confused anymore. 所以你可以看，其实我们上次给你们看的影片已经有看过，实际上这些一圈一圈都会长什么样子。那它其实就是每一圈线圈，它都会就是沿着那个线圈，它会制造出一个圆形 circular 的磁场线，这样一圈一圈的。那如果你现在在画磁场线的时候，你把磁场强度一样的地方跟磁场的方向一样的地方，你把它全部连起来， 然后你把它连起来之后呢，只要你越接近螺线管的中心，你就越会得到一个直线，因为上下对称嘛，以我们现在的状况，它上下对称。那么这就是为什么我们在分析螺线管的时候，我们就会可以说，这里的磁场一定是这样，一定是一条直线。然后呢，它们应该差不多，应该会是均匀分布的。但其实它有很多细微的结构，它其实没有那么的简单，那么的粗暴。这个是大家在实际应用的时候可以思考的问题。And in actual practical usages, and usually students or usually engineers or even scientists in the lab, and they get really confused about the magnetic field here and here, or even inside the solenoid, because if they just deviate a little bit from the center, and the strength of the magnetic field is changing dramatically. And if you are very close to your wire, and if you walk this way, then you can see that your strength of magnetic field is jumping up and down. And so people get really annoyed. It's very hard for them to do an experiment if the experiment needs the homogeneous magnetic field. So this is not very easy. Yeah, it's very difficult to do experiment with magnetic field. 所以，那我们现在在一般实际上面的应用，我们大部分时候还是会用螺线管去制造磁场。然后，但是你会发现说，其实如果想要一个很均匀的磁场，或是如果你的实验对于磁场的均匀度非常的 sensitive 的话，那个实验是很难做的。你在这边呢，你只要偏离一点点，磁场的数字变化就很大。那或者是说你很靠近你的 wire 的话，你在这个方向上面，你只要偏离一点点，然后磁场的数字就会上下跳动。所以做磁场的实验是很困难的。磁场本身它就不是一个会均匀的东西啦。从物理自然的意义上面来看的话，磁场它本来就不是一个为均匀而生的东西。好，所以做磁场的实验是非常非常非常困难的。好。This is solenoid. And this is toroid. I just leave it here for a while, and you can look at it. And then we have a little bit of water. I think teacher at the neighbor classroom is not using a microphone and he is shouting. Okay, this is toroid. And it's a little bit complicated, but let's analyze the flow of the current first. So this is our donut. Usually we use iron. Usually we use iron as the donut at the center. And if you don't want strong magnetic field, you can use plastic. You can use non-magnetic materials, or you can use a donut tube. And now this is a wire. We have the wire and we wrap it around our donut this way. So the wire is coming from here and going to the back of your donut, up and back, and go to the back and then to the surface. So I hope you can understand how the wire is wrapped around the donut. You can think about it. And if we do one thing, we just take 4 representative coils. 我们找4个线圈当代表。So number 1, 2, 3, 4. We take this one, this one, this one, and this one as the representative coils. Then we cut it to two halves, and we look at the cross section. So first we pick this one. So we'll pick this one, and we'll look at the direction of the current. So we start from here. So the current here is going. The current here is going into the wire. We can start from this one. So the current here is going into the wire, and the current here is going out of the wire. So all the current in the inner radius of your donut is flowing into your paper, and all of the current at the outer radius of your donut is flowing out of the paper. This is difficult, but you can just take the paper and you can draw it by yourself, and then you can understand what's going on. Let's start from this one. Okay, so all the current here inside, they are flowing into the paper, and all the current here are flowing out of the paper. And we just focus on the current here and here. You can use the right-hand rule, and you can look at the direction of your magnetic field microscopically. So if you look at the direction of your magnetic field here, we are having a current going inside into the paper. Yeah, this way. And the magnetic field is running this way. So if you look at a piece of magnetic field here, the direction is pointing to the top. But on the other side, the current is flowing into the paper. Magnetic field is going downwards. Yeah. So this is to the top. This is to the bottom. The current is exactly the same. The strength of the magnetic field is exactly the same, but pointing to opposite directions, isn't it? So the magnetic field inside, it just cancels to each other. And it's just exactly the same thing happening with this one and this one. And every pairs of coils, and they are just running the same concept. So you can have a conclusion that the magnetic field inside is very, very weak and negligible, because all of them just cancel each other by the directions. 所以这个有点复杂哦，但是如果你就是很有耐心的去应用右手定则的话，你就会发现，这是两个线圈嘛，它跟它们两个是两相对，然后呢，它制造出来的磁场是往上指。它制造出来的磁场是往下指，然后这两个呢强度是一样的，但是方向刚好相反，然后它方向相反就抵消。那这边也是用一样的想法，也是一样的状况。其他的线圈只要是这样两相对的，都是一样的状况。那么我们就可以知道说，其实在中间的磁场它们会互相抵消，然后最后全部都变得很弱，几乎可以忽略。它会有一些 up and down 就是会有一些小小的 fluctuation， 可是基本上就是到最后非常的弱，至少跟你中间的磁场比起来，它超弱的，你可以不要理它。那么 and out of the toroid, it's just exactly the same thing. So out of the toroid, the magnetic field is very weak too. And now we can just focus on the magnetic field inside the toroid. When you look at the direction of your magnetic field, and actually you can just link them together and you have a ring, isn't it? Like this. Just inside the coil, and then all of the magnetic field is superpositions, and they have the same strength pointing to the same direction, so they get stronger. They get connected and stronger. So that is the magnetic field of a toroid. 所以你看到螺线管的时候，你就会知道说这边的磁场很弱，外面的磁场很弱，但是这里面的磁场很强，而且它是连接成一个圆圈的形状。好，这就是为什么螺线管的磁场会长那样。然后有一些很盯紧，然后很仔细的人，就会开始对这边的细微的结构会很有兴趣。所以你也可以自己分析一下。他们基本上讲的就大概是这个样子。对，然后你也可以稍微思考一下自己会变成什么形状。它其实是很复杂、很细致的东西呢。做磁场 simulation 的人是很强的人。 So those theorists, when they are specialized in simulating the magnetic field, they are really, really strong. I find them really, really clever. Create a magnetic field with a specific field structure is a very professional technique. Really, really professional. It's much harder than creating an electric field. So usually you have to do a lot of simulations if you care about the detailed structures. Okay, so go on. Okay, so for the toroid, we are not doing the integration form right now. I'm not sure if we can do it. Usually we do it numerically, but now we can just apply the Ampere's law, because we already analyzed the structure of the field, and we can do some approximation, and we can take the Ampere's law for the magnetic field at the center of your coil in the donut. It's easier for us. And here's a dot indicating the current flowing out, and here's a cross indicating the current flowing in. And for the Ampere's law, this is the direction of your B, vector B, and it's just parallel to the direction of your integration. So the loop integral gives you B 2 pi r, obvious. Then this is equal to the number of the current on the coil. So this is easy too. And for vacuum or for the air, we use mu0. But if you have some feelings inside into the toroid, if you feel in irons and if you feel in any kind of material, then you have to go to your handbook and check what is the relative magnetic coefficient. Just simply multiply it and then put it here. Okay. So this is how the magnetic field works with complex structures. 所以我这里偷偷的往前进了一步，就是我们一般如果我们在处理是真空或者是空气的时候，你的 mu 这边我们就用 mu0基本的常数就好了。可是如果你的甜甜圈里面你是有塞东西的，就是你如果有塞铁磁性物质进去，如果你有塞一些介质进去的话，那你要去查一下你那个介质的相对磁化系数是多少，有一个 table 你可以去查。那你查到这个 μr 之后，你就把它 μ0跟 μr 相乘，把它放在这里就可以了。所以其实你在做磁场分析的时候，你真正的功夫大部分是用在分析你的线圈的形状，然后还有做 integration， 材料通常不是个大问题。其实跟处理介质里面电场有点像。我们大部分都是在处理几何形状的问题，处理几何形状比较麻烦。然后换材料的话其实还好，换材料就是介质系数换掉就好。然后磁场、磁化率，I'm thinking if I ever heard things like nonlinear magnetic constant. I don't think that I ever heard of it. Usually we put the stress on making the μr as large as possible. I haven't think of any researches on nonlinear behavior of μr. 我们之前有稍微提到，就是介键系数的时候，有很大一群人是在研究介键系数的非线性行为。就是你的 εr 不是常数的时候，你的 εr 如果是会跟着你的磁场一起改变的时候，磁化率 μr 的研究，我有听过有人在研究非线性吗？好像没有应该也是有人有在研究了，但好像没有那么受到瞩目。有一个原因可能是因为 μr 那个数字很大，就是 μr 的 scale 通常是什么几千几万，就很。大家的重心好像是放在如何把它变得更大，好像很少有人在研究μr是不是线性的，有点有趣，不知道为什么没有。我问一下我们系上研究磁性的老师好了，问他一下。 好 so this is toroid. And here's just this is a pictorial indication for you. So we just analyzed, actually we were so limited. We just calculated the magnetic field on this line. And we didn't have the time and we didn't have the skill to analyze the magnetic field here, and this is such a big deal. But we don't have the technique for the moment. And for the toroid, we just analyzed the magnetic field right here, but we didn't get any clue about the detailed structure here. Yeah, but if you're interested, and then you can just look around and then you can see how people calculate the butterfly structure of a solenoid. This is a big topic too. And I think for the toroid, because it's just a closed boundary, it's so closed and so compact, and so actually we don't have too much doubt about the distribution of the magnetic field. 好，所以其实你会发现我们刚刚算了那么多，其实我们算的东西是还蛮眼界还蛮狭小的呢。因为我们在螺线管上面，我们只有处理在轴线上面的磁场强度，我们都还没有办法去算这边跟这边的。对啊，我觉得应该是有，我不确定有没有 analytical 的 solution， 但 numerical 是一定有的，你可以上网去查一下。那螺线管的话，因为它的整体结构它非常的封闭，所以我会觉得这个圆圈状的电场就是圆圈状的电场，应该不会有什么太大的疑虑。主要是一些细部啦，就是一些细部的小小的结构。如果你有兴趣的话，你也可以去看一下专业的研究报告。Okay, so solenoid and toroid. So we finished the complex structures. Yeah. So here we just do a summary for now. So we started from the Biot-Savart law. We can use it to calculate the magnetic field created by current on wire. And here's another law. This is the Ampere's law. So you can put it into your big table. Yeah, so this is the end of our chapter 2.1. It's a long chapter. 2.1. This is a long chapter. And then we just analyze the field structure of magnetic field. But in the next chapter, we are going to work on the actual force. So how does magnetic force act on particles and how does it act on current? So this is our focus for the next lecture. Then I switch it to the other lecture, Untitled 2. Okay, so we just finished it. Here are the sources, but yeah, so just an introduction here. So for the magnetic forces, we are going to analyze the particles. How does the particle move? Or how is the magnetic force acting on the particles? How does it change the motion of the particles in magnetic field? And then from particles, we just go to current. So if the current is on the wire, and if the wire is straight, and if the wire is looped, and how does it move, and how is the motion going in a magnetic field? And finally, we are going back to the Gauss law. So we are telling you how this Gauss law is applying on the magnetic field. Okay. Here we start the charges in the magnetic field. And if you look at the picture, and probably you already know what's going to happen, but here is a video for it. You can see how the experiment is performed. Let's look at the videos.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in the uniform magnetic field. So this is an evacuated glass bowl, and there's an electron gun in it. An electron gun really just means a heated metal filament. It's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate that we put in a large positive potential that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bowl. The beam because it's exciting until it hits the glass.
His English is very fast. So here is these are the electrons flying in the space, and they get accelerated inside the installation. So that's the reason why our electrons can get flying like this. And you see the colors and you see the light because the electrons are colliding on the air molecules, and the air molecules are ionized, and those ionization creates plasma. And the plasma is the thing which radiates light from it. And that's the reason why you can see a colored line like this, and you can imagine on this pathway, this is just the electrons flying on this direction, and they have a certain speed. Okay.
Now you're seeing the beam because it's exciting a little bit of gas that's inside the bowl. You're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam. So you bring in a strong, concentrated magnetic field. But what we're here to do is to create a uniform field. That's what these two big coils are. So this is a large coil of wire on one side of the bowl, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here we'll just start turning it up, and you can see it start to curve more and more. And right now it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bowl. So we'll keep turning it up, more and more current, bigger and bigger beam field. Eventually, there it is. It makes a circle. Perfect circular motion, going right back to where it started. I'm going to turn the magnetic field back down to zero, straight through. So there's direct visualization of the circular motion of charge in the magnetic field.
So this is how magnetic field is working on our electrons. The electrons are not like they are attracted or repulsed by the force. It's not like this or like that. It's like this. So they are running in a way that they are sort of attracted, but the path is like going to the tangential direction, and they are running in a circle. They create a circular motion. So this is how magnetic field is working on charged particles. And this is the law. So magnetic force on a charged particle. We just focus on the positive charged particle now, but the negative one is just working exactly in the same way but in opposite direction. This is our charge. It depends on the velocity of our charge. This is huge. It depends on the velocity, not the acceleration. And this is the magnetic field. The direction of the force is an outer product. It's a cross product of the two vectors. So this is the strength of the force and direction of the force, velocity and magnetic field. And here is the picture. This is the pictorial interpretation of the mathematical form. You can just imagine in the experiment that we just saw it on the video. but with opposite direction, sorry. Because now we are analyzing the positive charges, but in the experiment it's a negative one, so the direction is just opposite. But anyway, so we have the magnetic field pointing into the screen right now. We have the cross. So now the magnetic field is vertical to the screen and is pointing into the screen. We have the positive charge here. It has a certain initial velocity, and when the magnetic field is applied, the force is acting this way. So the velocity is going to the top. The magnetic field is going into the paper. And if you apply the right-hand rule, if you do the outer product, you have the direction of the force pointing to the center of the dashed circle. So this is the direction of the force. The force is perpendicular to the velocity. The force is perpendicular to the velocity. And if your force is strong enough, then, no, I shouldn't say it this way. It's a circle anyway. It's a circle anyway, but the radius of the circle is controlled by the strength of the force. So it will create a circular motion here. Yeah. So the force depends on the velocity of the particle itself. It depends on the magnetic field. And it's pulling the charged particle and make them spin and make them run in a circle and create a circular motion. Well, this is really confusing for me. Okay, because it's not very intuitive. It's very confusing for me when I was in the university. It takes me such a long time to understand what's going on. And here's the introduction to the symbol, but I already introduced it. So for the vectors pointing out of the paper, we have a dot, and for the vectors pointing into the paper, we have the cross. So this is just an introduction, it's not a big deal. And I just applied the right-hand rule. So we can apply the right-hand rule to the force, to the velocity, and to the magnetic field too. Yeah. So the outer product is the velocity and the magnetic field, which is with your 4 fingers, and the direction of the force is just with the direction of your thumb. And here is some practical numbers. So first of all, this is the unit of the magnetic force. Or we should say this is the unit for the magnetic field, this is better. And the SI unit is Tesla. So Tesla is the Newton divided by the amount of charges, the coulomb, and the velocity. So meters divided by second. And we can rearrange it a little bit, and then you can get the units in the form with the current. So this is ampere. You just rearrange this one a little bit. But 1 Tesla is really, really big. It's not a realistic number in everyday life, actually. So we prefer to use Gauss. And 1 Tesla is equal to 10 to the 4th of Gauss. And this is a little bit confusing because usually we use order of magnitudes in the power of 3 order. The kilo, the mega, giga, if you remember, but for the magnetic field, this is the power of 4. 就是1 Tesla 等于1万高斯。1个 Tesla 在现实生活里面几乎不会存在了，那太强了，超强。对，那所以我们平常比较常用的是高斯。那你在做一些理论计算的时候，你要记得做这个单位换算，你要算对。And here are some magnitudes of the magnetic field just for your feelings. So the source of the magnetic field, the strongest one, from a superconducting laboratory magnet. I think this is something for the collider experiments, and they use such a strong magnet to bend the protons or to bend the electrons. So this is 30 Tesla. It should be again, and we just lost the sense in it. And the strong conventional laboratory magnet, so non-superconducting, the normal ones made of coils, the maximum is 2 Tesla, right? This is the number that I can imagine. And for the medical MRI unit, so if you have problems with your brain and then you have to go to the MRI lab and do the scan, this is 1.5 Tesla. I'm not sure if it's disturbing the signal in your brain, but this is really strong. Wow, this is strong. And for a simple bar magnet in everyday life, this is 10 to the minus 2. So you can see the difference in it. Wow. Okay, this is sort of dangerous. If you use the bar magnet made of rotaphone, the strong bar magnet, and sometimes if they are attracting each other, and sometimes if you accidentally put your fingers between the bar magnets, and sometimes your bones get cracked by the head. So this is the strength of the magnetic field. That you get a feeling. 就如果你在实验室你用的是乳铁碰磁铁，然后那个乳铁碰磁铁就是两个会这样会马上吸起来嘛。如果你刚好把你的手指放在中间，有的人的骨会被撞到骨折，所以你就知道那个有多强了。10个负2，10负2，1.52跟30还得了，好可怕。好 ，and then this is the surface of the sun, 10 to the minus 2. The surface of the earth, this is weak, 10 to the minus 5. Wow, so the magnetic field on the sun is very strong inside your brain due to nerve impulses, 10 to the minus 13. What's going on? I don't know, maybe they're doing some demonstration. Okay, so now you can have an idea about the magnetic field. Yeah. When I'm looking at the numbers, I always think of magnetos. Magneto. 或者你像万磁王，对，好，万磁王那个真的是很强，很厉害。万磁王跟他的对手是谁啊 ？X 教授是吗？然后那个是英雄联盟还是复仇者联盟？不是，那个叫什么？哦 ，X 战警，哦，对，好，对不起，我把他们全部都混在一起了。好，所以他们是三个完全不同的漫画系列。好 ，OK， 对我来讲这太困难了，对不起。但是我每次看到 Magneto 我都觉得哇，那很强就超强的，然后我以前在念书的时候，我们有个教授的名字叫 Magnus，M-A-G。N-U-S， 然后我们这些台湾人就帮他取绰号，我们叫他万磁王，很可怜，他都不知道为什么我们一直笑他，但是我们就笑一个学期。So when I was an exchange student in Sweden, we have a professor who teaches electrodynamics, and his name was Magnus. M-A-G-N-U-S, and then because we watched a film with Professor X and Magneto, so we just called him Magneto. So Magneto is running an exam next week, and we just make fun of him for one semester, and he didn't know what we were laughing at. Okay. So here's a comparison between the electric field and the B field. So electric field is usually created by plates, And if we create it this way, then we can have a electric field in a straight line, and it's evenly distributed like this. But the point is the charged particle inside the electric field is walking in a straight line, just in the same direction with the electric field. I should say that. It doesn't matter what the shape of your electric field is, but your charge is always moving in the same direction as your electric field. But for the magnetic field, then the motion is going to be very, very complex, because you already know the direction of your magnetic field, but your charge is running around in like a circle. But the other difficulty is usually the magnetic field is not walking in a straight line, it's walking in a curved line. So it's already curved, and the motion is also curved too, so you have to always think about everything in a circular motion. All the circles are sort of connected with each other. So the analysis is getting very, very difficult. It's not so straightforward as the motions in an electric field. Okay, and here are three questions, three important questions that can clear your mind. The first question is, we have two kinds of forces. Is it acting on a static or moving charge? So first question that you can ask yourself. And the second question is the direction of the force. Is it with respect to the direction of the movement, or is it perpendicular to the movement? Okay. And question number three. So the work, or you can say the energy required to move the particle, and where does the work come from? Does it do any work on the particle? So when we are analyzing the field and when we are characterizing them, we have to always answer the three questions. 所以这边有三个问题，就是电场跟磁场的差别。这三个是最决定性的差别。第一个问题是这股力，它是作用在静电荷上面，或是动电荷上面。是静的还是动的？然后第二个问题是，那它现在动起来了，它运动的方向呢，是跟你的场是平行的呢，还是垂直的？然后再来第三个问题是，在它运动的时候，你的这些场究竟有没有对它做功，或是你需不需要能量去推动这些 particle 的移动？好，在磁场上面，这其实是一个非常非常 confusing 的问题。好，你想一下就知道为什么对磁场而言，大家会觉得哇，这个问题很 nasty 很奇怪。然后这个在物理学上还是谜哈。那我们这边来给一下，我们来讨论一下答案。So for the electric field, it's working on static and moving charges. So for the static charges and the moving charges, and it's all of them it's working. But for the in case of magnetic field, it only works on moving charges. On static charges, magnetic field doesn't work. 所以对静电荷来讲，磁场是没有作用效果，无效。磁场只对在动的电荷会有影响力。那电场的话，不管是静电荷或者是动电荷，它都是有某种程度的影响力的。And in the electric field, the charged particle is moving in the same direction as the electric field. The force is parallel to the electric field. But for the magnetic field, the force is perpendicular to the magnetic field. 所以一个是平行，一个是垂直。And let's just think about the work, the kinetic work, I have to say. We just focus on the kinetic work. So, does the electric field doing kinetic work on the particle? The answer is yes, because our force is parallel to the direction of the movement. You can think about the definition of work. So that is the energy that required to push your object to move And we are always calculating the energy required for the parallel movements. So we always insist that the force should be parallel to the direction of the movement. But somehow we create a big mistake for magnetic field. You can see that the force is really acting on your particle. The direction is perpendicular to it. It creates a circular motion, but it doesn't do any kinetic work on it. And this is confusing. It really takes energy to create your magnetic field. And your charged particle is really moving. So I think philosophically, we cannot say that magnetic field is not doing any work. But if you stick with the mathematical definitions, you have to say that the magnetic field is not doing any kinetic work on your particle. 所以这个大家常常吵架。这个是当初我们在定义功这种东西的时候，因为那时候的人不知道嘛，16世纪的人，然后就捅了一个大篓子，然后到18、19世纪开始发现，有磁场这种东西的时候，就发现糟糕，我们的理论出了一个大问题。因为呢，我们在定义功这种东西的时候，我们定义的是，我推某个东西一下，它往某一个方向往前走，然后呢，它往前走啊，我设定了我的力跟我的运动一定要是同一个方向，所以大家是用这样子的概念去想功这件事情。可是到了磁场的时候呢，你看实际的状况，你会发现，我的力确实是有作用啊，然后我的 particle 确实是有被我的力影响转了一圈啊，然后我去制造我的磁场也是需要用到 energy 的啊，你 drive 你的 current 是需要 energy 的，那你为什么会说自己没做功？好奇怪啊！所以在这个部分呢，其实在物理学上面，这是一个算是物理哲学上面的一个大漏洞啦。就是在哲学上，你不能说磁场没有做功，只是说它做功的那个方式跟形式跟我们数学上面的定义就是有打架，这样有听懂吗？好，对，所以大家看到课本上面讲说磁场没做功，然后或者是以后学电磁学的时候，应该还是会有人跟你们讲说磁场没做功，考试的时候也会跟你说磁场没做功。大家心里面要知道说这件事情它纯粹是哲学上跟数学上面的打架，它不是你不要太纠结，就是不要对那件事情太纠结。这件事情这个问题会爆出来，纯粹是因为16世纪的时候，人们在定义功这个东西的时候，他们的观念是很狭隘的，就是他们的观念只会想到说，我一个力这样子推出去，我的物体一定要跟我的力是同一个方向。可是电磁学的发展跟发现磁力的时候，那个时候已经很久以后了。对，那人的认知本来就是会一直不停的扩展的，所以磁场它其实是在机械功上面这个东西，磁场它算是一个例外。好，所以大家可以用这种比较包容的看法去思考这件事情。对，所以常常会吵架，就是这边常常会在那边争论说磁到底有没有做功。我会觉得那个问题有一点，我觉得不需要这么心胸，不要这么狭隘。对，它纯粹只是一个定义上面，因为当时的人不知道。然后我们现在已经是20世纪了，21世纪，我们可以把我们的心胸再放宽一点。好 ，OK。So I think this is this is getting complicated. So I'll do it in the next lecture. 这个问题它不难，但是很有趣，所以我下次上课再讲。那我们今天上课先上到这边，感谢大家。